Hello everyone, welcome to this talk about using optimization insights to solve positive LPs faster in parallel. This is a joint work with Lorenzo Arecchia. Alright, so to begin with, what is positive LP? Positive LPs actually consist of two cases. Case 1, packing linear program packing LP. That is to maximize 1 transpose X, subject to the constraint that AX is less than or equal to 1 in the vector sense, and X is a non-negative vector. So here, this LP is for the packing LP because each entry of this matrix A is also required to be non-negative. Okay, so this is packing LP. Throughout today's talk, I'm going to use M and N to represent the number of rows and columns of this matrix. And here, a quick remark. There's really nothing special about the two vectors 1. So, in fact, in the more general, but in fact the equivalent forms of packing LP, one can replace the use of 1 with any arbitrary positive vectors. So, because they're totally equivalent, in the rest of the talk, I'm only going to focus on the standard form, which is the one on the top. All right, so this is packing LP. Its LP dual is the so-called covering LP. And these two together is known as positive linear programs. And this is the names are due to Luby and Nielsen back to 22 years ago. In today's talk, let us denote by opt the optimal value of both of these two programs. So in fact, this pair of LPs is mathematically equivalent to another form of positive linear programs, which is the so-called saddle point form. So imagine that there are two players. The X player, the red one, is interested in playing a probability distribution, and he wants to minimize. And the Y player, the blue one, he wants to maximize and also play a probability distribution. And they want to jointly compute Y transpose AX. So the optimal pair of solutions, X and Y, are actually known as the mixed Nash equilibrium for this two-player matrix game. And if one does some careful analysis for maybe 3 minutes, we realize that actually the optimal value of this saddle point problem is precisely 1 over opt. So this is one of the reasons these two problems are totally equivalent. So at this moment, I'm really willing to bet like $20 to say that anyone listening to this talk must have at least seen one of the 3 forms, which hopefully is a good sign that this is a very important problem to study. But what is more, packing LP actually is related to many of the sub-areas of theoretical computer science. And for instance, if, just by opening up this box of approximation algorithm, people have actually used the positive LPs to solve actually a bunch of approximation problems, including like bipartite matching, max set, and so on and so forth. Okay, so at this moment, hopefully, like you're convinced that positive linear programming is an important problem to study. For convenience of today's talk, let me just focus on packing LP. Okay. And the solutions to actually covering LP its dual is sometimes more involved, but for simplicity, let me only focus on one side of the problem. So packing LP is by definition a linear program, so one can use, say, the simplex method or the interior point methods to solve it, but those methods are typically very slow. They require the inversion of a matrix. And therefore, for today's talk, I'm interested in approximately solving it. That is to obtain an epsilon approximate solution by finding a positive vector which is feasible. That means AX is less than or equal to 1, and its objective value 1 transpose X is larger than or equal to 1 minus epsilon times opt. And in particular, I am interested today in finding nearly linear time algorithms to approximate packing LP to constant approximation ratios. So there have already been papers and algorithms achieving so. In particular, the above 4, originally discovered by Luby and Nielsen back to 22 years ago. in which their total running time are nearly linear. So the running time is the big N, the number of non-zero entries of the matrix, multiplied with a few log factors and divided by a few epsilon factors. So this is great. The total running time is fast. And what is even better is that all of these 4 algorithms perform in a polylogarithmic number of iterations, and each of these iterations is essentially as heavy as the matrix vector multiplication that can be implemented, for instance, in logarithmic depth. So in total, like the algorithms can be implemented to run just in polylogarithmic depth, and this is why, at least for these 4 algorithms, they're known as the parallel solvers to this packing LP. So parallel solvers stand in contrast to actually another interesting line of research, which focuses on sequential solvers with better total running time. But these, like for instance, these 5 papers obtain algorithms whose like total number of iterations is at least linear. And for today's talk, I'm going to focus on parallel solvers. Okay, so here is the quick line to summarize what we have obtained. So we have obtained the first approximation algorithm for packing LP that has a convergence rate which is epsilon cube. So this is in contrast to all the previous results, which converges only in epsilon to the 4th power or even worse. So it has actually been raised as an open question that has stood for essentially 20 years about how to go beyond this epsilon to the 4th power, because even the original algorithm of Lubin-Nissen has already achieved so. And in short, we have broken this epsilon barrier. All right, so let's now see like how we designed an algorithm to achieve so. So it's going to be an extremely simple algorithm having only 5 lines. I even managed to tell my mom what the algorithm is, and there aren't too many algorithms in my lifetime that I have achieved so. So line 1, okay, initialization to choose a vector x that is positive but small enough, satisfying ax less than or equal to 1. So this, believe me, it's going to be very simple. So line 2, choose some parameters, mu and alpha. So don't need to remember like how they look like, but essentially they're both less than or equal to 1 and having a few log factors and a few epsilon factors in it. Okay. Line 3, perform a for loop with how many iterations? In fact, this big T, that is log square over epsilon cube number of iterations. That's actually what we promised on the previous slide. And line 4 is now really the important meat of the algorithm. The first 3 lines are essentially simple. The 4th line is about, for each coordinate I, let us compute a feedback value, Vi, using this formula. So there are actually only 2 things important about this feedback value. You don't need to remember the form, but one, you need to pay attention that the computation of this Vi is extremely simple. It can be implemented to run in just linear time because it's basically 2 matrix vector multiplications. And the second, each feedback value is at least -1. But it may be very large, like it may go to positive infinity. Okay, so now comes to the 5th line. That is, for each coordinate I, we change xi multiplicatively by a factor that is e to the minus alpha times the so-called truncation of Vi. That is the mean between Vi and 1. So the truncation function does nothing but if Vi is larger than 1, I truncate it to 1. Otherwise, I don't touch it. I output the same value. Good. So this is really like how simple our algorithm is, except one place. That is, I'm hiding a 6th line. That is an end for sentence. Okay. So that's everything about our algorithm. So as promised, we have used only this number of iterations, and the total running time is also what we promised. So for the rest of the talk, you don't need to remember the algorithm because I promise that I will always put it on the top right of the slide. There are 5 lines, but the other 3, are simple, so we only need to remember 2. And now let me really make an important remark. So far I have told you about how the algorithm looks like. So what is really complicated behind it is the convergence proof. So I want to claim, before I go into any technical detail of our proof, that our analysis is actually very different from all the previous results in the following sense. Here is how all of the previous parallel solvers work, both in terms of the algorithm and in terms of their proof. So they divide the algorithms into groups of iterations. Each group contains up to a log factor 1 over epsilon square consecutive iterations. And then they have a total of 1 over epsilon square such groups. So this is why all of the previous results cannot overcome this 1 over epsilon to the 4th power bottleneck. So the reason they need this is because the analysis of all those previous results are very combinatorial in nature. So their algorithm, or their convergence proof, essentially works as follows. So for each group, I want to make sure that I can make some progress. So then how can I show this? So I prove by way of contradiction, if I do not make progress, that's good enough. Then that means in this group of 1 over epsilon square consecutive iterations, I must have changed the coordinates too much so that one constraint is violated. And for each group, I find 1 constraint, and I continue to make arguments like this. So it's very combinatorial in nature. What we will do instead in the rest of the talk is to use convex optimization. That is, we would develop new techniques from optimization and then apply it to packing LP. At that moment, it will become clear and automatic why we choose the feedback value to be this and why we need to do this truncation. Okay? So for the rest of the talk, let us go into the optimization world. Good. The first step of doing any convex optimization is really to reduce the problem into a purely minimization problem. That is, we want to minimize this function f mu defined over all the positive vectors x. And mu is a parameter, and this f function has really 2 components, the red one and the blue one, and we wish to minimize it. The reason for having this blue one is really obvious because originally we wanted to maximize 1 transpose x. So now we should really minimize negative 1 transpose x. And the red part is in fact the so-called exponential penalty function for ax less than or equal to 1. So as you see, we no longer require x to satisfy ax less than or equal to 1, but instead we replace it with this exponential penalty function, which, as one can see, just by the definition and actually our choice of mu, then as long as 1 constraint is violated by a little bit, then this penalty function will be very large and will totally destroy the gain of the blue part. So this is kind of the intuition. That's why we define this function. And now let me state, without proof, that first of all, this function f mu is convex. Second of all, its minimizer is roughly on the magnitude of minus opt, plus or minus at most an epsilon factor. And third, from this moment on, I claim that it really suffices for us to obtain a vector x, satisfying that its objective value fx, when comparing to the minimizer fx star, whenever this difference is less than or equal to epsilon times opt, then I claim that this vector x is an approximate solution, an epsilon approximate solution to the original packing LP. In other words, from this moment on, we can really forget about the original packing LP and only focus on this convex function and try our best to minimize it. Okay? So let me now make a quick and interesting remark, which is our feedback vector and feedback value vi is in fact nothing but the coordinate gradient of this function f mu. And this is actually why we designed the feedback value to be so, because we want it to actually be the gradient. As a result, we can now simplify our algorithm, and we can simplifying it to the following two short lines. So let us now really go to the analysis to see how we managed to show the convergence. So the key idea is to decompose the feedback vector or the gradient vector into the summation of two components, Xc, the so-called truncated gradient, and eta, the so-called large gradient. So here, the way we define Xc, we only need to define Xc because eta will be the remaining part. So we define Xci for each coordinate I to be the truncation of Vi. Pictorially, it says whenever Vi is larger than 1, we truncate it to 1 and define Xci just to be 1, and we define eta to be the remaining, so that they sum up to Vi. Or if Vi does not exceed 1, we define Xc to be the same as Vi and eta to be 0. Similarly, for Vi being negative. Okay, so at this moment, it's clear that Xc is a vector whose components are between -1 and 1, and eta is a non-negative vector whose components could be really huge. This is what we call the gradient truncation technique. The reason we want to apply such a gradient truncation is because it allows us to apply the so-called gradient descent method to the large gradient part, and the so-called mirror descent method to the truncated gradient part, and then apply what we call gradient mirror coupling technique that we developed in a separate paper in order to combine the convergence analysis of the two smaller methods in order to get a faster global method. So that is like the overall plan of the rest of the talk. So before I go to the next slide, let us pay attention that this truncation function is actually nothing but Xc. So as a consequence, I can even further simplify the algorithm into this little box. So let me now really define what gradient and mirror descent are. Gradient descent, in the language of optimization, is in fact a class of lots of different methods that guarantees to decrease the objective, the convex objective, step by step. That is, the objective value gets decreased after every single iteration. So if we denote by x0, x1 until xt, a consecutive of t gradient steps, then almost all gradient descent analysis works as follows. They show that in every single step, one can decrease the objective by an amount which is a factor that depends on actually what the algorithm is, multiplied with the inner product between the gradient of the function at the current point times the difference between the current point and the minimizer. So the reason that gradient descent cares about this type of inequality is really because the right-hand side, the inner product, is an upper bound, a positive upper bound on how much difference I am still having until I could reach the minimizer, which is the difference between the objective value of the current point and the minimizer. So in our case, we actually managed to show that our update rule is one type of gradient descent, except that we proved something slightly weaker. That is, although we are having a good factor, which is alpha over 4, a constant factor, however, we cannot make a good progress proportional to the full gradient, but we can only make it proportional to the large gradient. So therefore, we need a separate method to deal with basically the small gradient. This is the place we use the so-called mirror descent. So mirror descent, due to the time limitation, let me say that it's really a generalized version of the famous multiplicative weight update scheme. As you know, because our update rules are multiplicative, so it really naturally fits into this framework. And let me state without proof that using mirror descent analysis adapted to this problem, actually we can get the following type of upper bound. So for those of you that are familiar with the notion of online learning, in fact, the left-hand side is the so-called average regret, and one can get a good upper bound to it. So what is important here is not how we deduce this upper bound. It's in fact instead that for classical mirror descent, what we put here is the full gradient of the function. But what we can show is only with respect to the small gradient. Okay, so this is a major difference between our analysis and the classical mirror descent. And I agree that we're proving something weaker because we are only getting an upper bound for the small gradient, the truncated gradient. Okay, so to sum up, we have two kind of partial algorithms, one having some progress proportional to the large gradient, the other one having progress proportional to the small gradient. So now, it's really a natural guess about what to do next, which is, remember that we have our full gradient being the summation of the two. The full gradient equals to the sum of the large and the small one, and therefore we can just apply the above two lemmas that I stated without proof to upper bound each one of them. And then just by choosing appropriate parameters to balance the two steps, to balance the gradient and mirror descent steps, one can get a good upper bound that's epsilon opt to this quantity. And on the other hand, if one lower bounds it properly, he can see that we're essentially done. That is, we have obtained a point x to the t minus 1, whose objective difference between that point and the optimal point is at most epsilon times opt. In other words, we have obtained an approximate minimizer to the function. And as I have described actually back to the beginning of the talk, it really suffices to us to find an approximate minimizer because that gives us an approximate solution to the original packing LP. So let me now really make some quick conclusion here. That is, I want to say, in the theory of optimization community, here's I find out how most of the papers are written. They begin by defining an important class of functions, such as the class of smooth convex functions, and then try their very best to design the optimal method for that class. In contrast, in reality, we may be more interested in individual problems. For instance, in today's talk, the packing problem, or more generally max flow or scheduling or other problems. So in the past 10 years, there has been actually a very successful trend of papers that managed to do this, which is to reduce the problems below to one of the big classes above, and then to apply the optimal method for that bigger class to those individual problems. So, but I personally find this path not maybe as effective as it may look, because many of the problems below, for instance, the packing LP of today's talk, does not fall into any of the good categories above. For instance, our objective is not smooth. And even if one tries to use some, say, smoothing technique, he will really lose a lot in this path. Moreover, perhaps more importantly, even if one problem below just falls directly into one of the big classes above, however, applying the optimal algorithm for this bigger class to this individual small problem, you may not get an optimal algorithm anymore. So therefore, I am personally very enthusiastic recently about an alternative path of designing algorithms, which is to both abstract away and design new techniques from the optimization theory. For instance, in today's talk is about the coupling technique and the gradient truncation technique, and then apply those techniques to individual problems. So this is like, you know, preparing some pre-cooked meat, and then everybody could really like go to the supermarket and buy the pre-cooked meat, and then go home to add your own ingredients to cook your favorite soup for your own dinner. So I find like this path being actually very successful, not only in today's talk, but also in a few other works of ours. So I hope that more people can join us in this course. So to really sum up, we have obtained this line of algorithm in today's talk, and I have skipped the detailed analysis for the gradient and the mirror descent lemmas, the two lemmas. And I have also skipped the details for what to do for covering LP. Both of them require actually very interesting techniques that I'm skipping here. So I strongly encourage everyone to read our paper. And the last thing, that is a quick advertisement. Remember that there's another line of research for sequential solvers, and we obtained actually a separate paper that we put online 2 months ago. So we put online an algorithm that runs in 1/epsilon convergence rate for the first time in the literature. So the best known convergence is 1/epsilon square, which has also been open for 20 years about how to improve it, and we obtained the first 1/epsilon convergence. That paper also uses, for instance, our pre-cooked meat here, which is the gradient truncation, and actually a host of other techniques as well. So thank you very much for your attention, and here is the QR code for our paper.